Hello everyone. So today I will be discussing three set of questions. One is from 2019, the other two are from 2018. So I think we have to start. Before starting, I will introduce myself. So I am Anjali Negi. Currently, I am a PhD student in IIT Kanpur in Physical Chemistry department. So yes, all of you can see my screen. Okay. So it was proposed that there is one transition state exists and it was denoted as AB dragger. So we can actually write the above reaction as A plus B is in pre-equilibrium with transition state AB dragger, and finally this gets converted into the product P. Here rate constant are K1, K minus 1 and K2. So the points to note here is one, that there is pre-equilibrium between the reactants and transition state. Number two, that to actually apply the equilibrium approximation, it can only be hold true if K2 is very slow. So
it holds true if K2 is very slow. That means my product formation is much slower. And the third point to note here is that this transition species or the activated complex denoted as EduUdr is a short-lived species. And once it vibrates along a particular degree of freedom, that is, along the reaction coordinate, this will get convert into the product. And along a particular degree of freedom, that is along what direction? Reaction coordinate along will give me product or completes the reaction. Now the question is that what do I mean by the vibration of AB? Like what do we understand by the vibration of our transition species or activated complex? So to understand that, let's draw the two-dimensional contour diagram of the potential energy surface for our reaction. So remember, so earlier I have denoted here A, B, but just for to give more insight, I will be writing my first molecule as a AB molecule, this one as a molecule C. So my transition species become A, B, C, and my product will be BC plus A. Okay. So here the reaction coordinate along x-axis is RBC and along y-axis is RAB, so that here I have okay. So here I have R equilibrium AB and here I have R equilibrium BC. So what this is a two-dimensional contour plot for the potential energy surface of the reaction, and my REAB is nothing but it corresponds to the equilibrium bond distance of AB molecule. Equilibrium bond distance of AB molecule. So this will be AB plus C, and similarly REBC will be the equilibrium bond distance of BC molecule. So this will be BC plus A, correct? And for the reaction, so it follows the direction from AB to actually going to BC. So something like that. And so let's say it starts from here and goes to here. And there, if I draw some contour plot, something like this, the potential energy surface in two-dimensional is the contour plot. So there is one intersection.
NOBR2 wasn't there in the beginning and it's not there in the end. We call NOBR2
Okay.
an intermediate.
So if there is one intersection region, so that will be my the crossing region for the transition state, correct? So this is actually the how the energy diagram looks like for the reaction. It is simply something like like this. This is my reactant, my product, and here I have my transition state. And the barrier here is whether we can call it activation energy EA, or in Eyring equation it is actually denoted as E. Also there is one correction for the E where we take actually the vibrational zero 0 point energy for the vibrational state of the both reactant and transition state. So that comes as E star. So that is a little more detailed, so we will not go into it. So here, for this region where it is a crossing for a region for the transition state, so what is the motion looks like in this region? So for that, if I just draw the reaction path, okay. So to cross the barrier, now right here, the kind of motion that we have, that the reaction is moving actually diagonally, okay. So what will be the coordinate here? So in x-axis, my BC bond vibrate. It's just the vibration of BC bond, and along y-axis we have vibration of AB bond. So initially, if I had just AB plus C molecule getting A plus BC, so what kind of vibration I was having? Only two, that is the vibration of AB molecule and the vibration of BC molecule. But near the so this is actually for, if I just say that this is my zone 1 and this is my zone 2. Okay, so this is where in the zone 2 only, and this is for zone 1, correct? That only BC vibration is there in zone 1 and only AB vibration is there in zone 2. But near the transition state area, that is near this region, what kind of vibration I will be having? So near transition state, I have structure like A, B, C, correct? And neither of the bond is actually broken nor made. So this is what a transition state. So the points here to note is the activated complex has two bonds here. So it gives us the possibility of actually two kind of vibration. One is symmetric stretch, the other one is asymmetric stretch. Correct? Now, so this was my reaction coordinate RBC along X and RAB along Y. If I just look along this direction, the reaction will be, my transition species will be having what kind of vibration for this particular direction? It will be having, see, it will be having a symmetric stretch. Okay, and exactly orthogonal to this, that is this arrow, I will be having anti-symmetric vibration. Okay, so this will be so like when my BC bond get contract, है ना? So my AB bond will just elongate or vice versa. Okay, so here the point is that along the transition state, it's neither it's neither AB or BC bond vibration, but it's a normal mode, that is both that is the vibration of both AB bond and BC bond, but not isolated. So that is what a normal.
I didn't get that. Could you try again?
So the second point is that is along the transition state, it is neither RAB, it is neither AB or BC bond vibration alone, but it is a vibration of the both the bond together, and that is what a normal mode is. So it is it actually goes with the orthogonal direction, that is the symmetric antisymmetric stretch. So the reaction happens along this blue arrow, and this direction is actually the antisymmetric vibration. Antisymmetric vibration. Okay, and this gives me antisymmetric vibration, which will give me the product. But so till now, what we have said that so what is the conclusion till now? So the conclusion is that the ABC has a set of vibration, and it can so the conclusion is that my transition state is does have a set of vibration, that is it gives rise to the normal modes, and so it can be actually have a symmetric stretch or antisymmetric stretch, but only the antisymmetric vibration will give me the product. Okay, so how does the coordinate of my antisymmetric vibration looks like? The coordinate along this arrow is something like RBC minus RAB. So this is a coordinate transformation at the transition state. Also from geometry, you can actually see that we are actually crossing the transition state in our potential energy surface diagonally. And the second point is, and the third point is that my transition species actually only survive over the time period of asymmetric stretch. So what happens is that in general, there will be one particular vibration which we know is antisymmetric in nature, will give me along the reaction coordinate will give me product. So for example, the frequency of the reaction, which is K2, nothing but identical to the characteristic frequency mu trigger along the reaction coordinate. So you remember A plus B with the transition frequency is in transition state is in pre-equilibrium with the reactant, and finally gives me product P with K2. So my K2 is actually it depends upon nothing but it depends upon the characteristic frequency mu trigger, which is along the reaction coordinate, and this frequency is a low frequency vibration of my what? Transition species, correct? Because, and why? Because for equilibrium expression to be valid, the K2, that is my rate of product formation, it has to be slow. So hence, coming back to my question, yeah. So the Eyring transition state theory for a bimolecular reaction. So please note that we have asked the activated complex has. So we need to think about that. So what does our activated complex has? No vibrational degree of freedom. So that cannot be correct. Vibrational degree of freedom, but they never participate in product formation. That is also false. And one high frequency vibration that lead to product formation. But we know that the frequency that our activated complex is associated with is actually a low frequency vibration. Okay, so that is also false. So the correct option is one low frequency vibration that lead to product formation. Okay, and that is also is asymmetric in nature. For this particular topic, I will strongly recommend you to just watch the Introduction to Biomolecular Reaction Dynamic by Professor Arijit Kumar Dev, Department of Chemical Science, IISER, Mohali, and I am also attaching the link. Thank you.
Yeah, so if you guys have any doubt.
Madam, I'm talking Saravanan, madam.
Yes.
Madam, that the last question is hiring your bimolecular reaction. No question asking. No, that is one more time explain for me, madam. Answer, madam. I want.
So what do you want me to answer? Your question is?
Sir, last question. No, you explain. No, that is 2018 question. Hiring a bimolecular reaction.
Yeah, so I have just completed the video. So you want me to explain it once more? So you want me to explain it again?
Yes, madam. Yes, madam. Yes.
Oh, okay. So I will just make it quick because you can access the video later also. So I will just
Okay, madam.
share my screen once again. So you can see the screen.
Yes, madam. Yes.
So the concept behind the Eyring equation is based on the transition state theory, and the transition state theory is just if you see here, that it is just the for example, in this question we were asked about the bimolecular reaction. So if I have two molecule A, B giving me product P, but because
Yes.
it's a transition state, so there should be one transition state in between, so it is AB dragger. And yeah, in transition state we assume that my transition state is in pre-equilibrium with my reactant. So that is the pre-equilibrium is set up here, and finally I get the product with the rate constant K2. So actually the assumption between pre-equilibrium is that my product rate, that is K2, has to be very slow, and because that is a rate determining step, it is slow. And the pre-equilibrium that is set up in between the transition state and my reactant, you have to find out the concentration of the transition state, and then finally you have to find out the rate of the whole reaction. So this is what a equilibrium, pre-equilibrium conditions are. So we were asked about the my question was that the activated complex has. So I have actually explained a lot about how this activated complex convert into the product. So in short, when you go through okay. Yeah, so in short, when you go through the potential energy surface of my reaction or bimolecular reaction, so it seems like this is the reaction coordinate along X for the BC bond vibration of BC is the product, for example, and AB is my reactant. So AB is initially reacting in zone 2, AB was reacting with C, and then my AB bond gets broken and my BC bond gets formed. So this is the direction of my reaction, okay, in this arrow. And the contour plots actually intersect here, and that is what we call the crossing point for my transition state. So my transition state here, we need to find out what kind of motion my transition state is doing here. So if I just follow the reaction path, it will be along the diagonal, something like this red color arrow. So yeah, so finally what happens is that, okay, so here I have discussed that this red arrow shows the symmetric vibrations, because this ABC transition state is something where neither any bond is formed, neither any bond is broken, correct? So this particular, yeah, so that's particular transition state. You can have two kind of vibration, I mean symmetric and anti-symmetric, both are possible, but what will give me the product? The anti-symmetric vibration only will give me the product. And that why? Because the reaction path that we were following, my transition state, direction of my transition state was in direction of this blue arrow, and you can see that this direction is corresponding to the anti-symmetric stretch. You can just, yeah, this purple line that I have shown is that this is the BC bond vibration coordinate, so it gets compressed here and my AB get elongate, so that my BC bond is formed and AB bond gets broken. So that is we actually concluded that what happened, that along this blue color arrow I have this kind of coordinate, and this is the corresponding one this is the only one vibration, which is the anti-symmetric vibration, gives me the product finally. And this particular vibration is the nature of this vibration is slow, so the frequency that is associated with this, that is mu dragger, is slow frequency. So finally,
Yes, madam. Okay.
yeah, so finally that we see here, that one low frequency vibration will lead to the product formation.
Okay.
Yeah, okay.
Thank you, madam. Thank you, madam. Thank you.
Also, I will like to ask you one question, all of you. What do you guys have answer for this question of like what is the difference between one intermediate and transition state? You can answer in the chat box also. Yes, Sarvanan.
Madam, that intermediate is very, that is intermediate, no, madam. Intermediate is very, that is double decade, that is activated complex, madam. This is one, madam.
Anyone else?
Intermediates have some longer lifetime than the transition states. Transition states are very short-lived. They cannot be identified. We assume that they might be in this form.
Yeah.
But intermediates we can identify and isolate.
So yes, so in video, if because it was a lengthy video, I don't know you guys have noticed it, but I have mentioned that the lifetime of my transition species is actually the one single bond vibration is equal to the time period of one single bond vibration, that is the antisymmetric stretch for the product formation. So you can just think that how small lifetime it will be, because it is just it has the time period of the bond vibration, only one single bond vibration. So that is as for the transition species. But again, you are correct that for intermediate we have a longer time period, and yes, so that is there. So okay, so let's jump into another question. Question 40, no, question number 51.
Hello everyone. In this video, I will be solving the 2019 chemistry question number 51. This question states that for a bimolecular gas phase reaction, the pre-exponential factor is given, and we have to find the standard entropy of activation at 25 degrees Celsius, and other constants value is also given in the question itself. So to solve this particular problem, we have to use the Eyring equation, which gives us the relation between reaction rate and temperature. Okay. So this equation gives us the transition state rate denoted by KTST. So KTST is actually equal to KBT, that's the Boltzmann constant, multiplied with temperature divided by Planck's constant H, exponential to the power minus delta N Draeger plus 1 multiplied with exponential delta S Draeger upon R multiplied by exponential minus EA upon R2. So here delta N Draeger is the change in molecularity in the given reaction. Here delta N, we can also write it as the change in moles between transition state and reactant. So for example, in the given problem, we have P plus Q. So if PQ is my transition state, it gives me the product R. So here the molecularity for the transition state is 1. Molecularity number of moles is equal to 2 in the reactant side. So my delta N Draeger, the change in molecularity becomes 1 minus 2, that is minus 1. So my exponential here becomes e to the power minus 1, that is plus 1 plus 1, that is e to the power 2. Correct? Also, we need to find out the pre-exponential. We need to find out the uh, uh, S entropy term. So, for that, we also know we have another equation called Arrhenius equation, which also gives us the relation between the reaction rate and temperature. It is given as K is equal to A e to the power minus EA upon RT. Correct? Yeah, I will just write it here. On comparison, we get this part as equivalent to a pre-exponential factor A. So hence we can write A is equal to kBT by H e to the power 2 and exponential to the power delta S Draeger upon R. Now, once we put all the values given in our problem, that is exponential 10 to the power 13, small k. So this is Boltzmann constant 1.38 into 10 to the power minus 23. Temperature, that is 298 Kelvin. In a Kelvin scale we have to convert the 25 degrees Celsius, and here 6.62 into 10 to the power minus 34. This is E exponential delta S Draeger upon 8.31. Once we solve this, we get delta S Draeger as minus 12.57 joule per Kelvin per mole. So the answer for this is minus 12.57 joule per Kelvin per mole is my standard entropy of activation. For this particular topic of bimolecular gas phase reaction, I will highly recommend to go through the lecture Chemical Kinetics and Transition State Theory by Professor Amber Jain, Department of Chemistry, IIT Bombay. Here is the link for the lecture. Thank you.
Yes, any doubt? Okay. So actually the if you want to go understand the concept more, because I am trying to explain you the basic. So the lecture that I am attaching and giving reference to is actually very beneficial to you guys if you want to have in-depth concept of that topic. So okay, I will share another.
Spine. Hello everyone. In this video, I will be solving GATE 2018 Chemistry question number 40. This question states that for an inverse spinel AB2O4, the A and B respectively can be. So before moving, we have to look what are actually spinels, inverse spinels, and how to identify inverse spinel. So, spinal structure is a series of compound having combination of two oxide so it is a mixed oxide of divalent and trivalent metal ion. Okay. By saying divalent, that is A plus 2, it will form oxide AO, and a trivalent metal ion like B plus 3 will form oxide B2O O3. So my spinel will be AB2O4. Okay. Now there exists two type of spinel. One normal spinel and other one is the inverse spinel. So for normal spinel, the spinel structure is such that the oxide ions are arranged in CCP is such that oxide ions are arranged in cubic close packing CCP, and divalent ion is present in 1/8 of tetrahedral void and the trivalent ion is present in half of octahedral void. Okay, so this is the normal spinel. We can write it as this A, which is a divalent. It is present in tetrahedral void. B, which is the trivalent metal ion, present in octahedral void with O force. Similarly, in inverse spinel, so in inverse spinel, what will be my trivalent ion gets distributed equally among octahedral and tetrahedral void, okay, and my divalent metal ion, that is A, is occupy the octahedral void. Okay, so here my trivalent ion is equally distributed between tetrahedral and octahedral void. Okay, so to distinguish between these two, to identify the spinel, we take the help of crystal field splitting energy, that is CFSE. So we calculate the CFSE of both the metal ion, that is divalent and trivalent, and then compare these two such that if my B plus 3 CFSE in octahedral field, if it is greater than the CFSE of A plus 2, it will be a normal spinel. So similarly, if the CFSE of my trivalent metal ion is less than the CFSE crystal field splitting energy of my divalent metal ion, then it will be a inverse spinel. Okay. Let's just note some tips. Number 1, that the CFSE of a non-transition metal is 0. And number 2, if both A plus 2 and B plus 3 metal ion are non-transition transition metals, then they belong to normal spinel. Okay. Now, talking about the crystal field splitting energy, CFSE, in octahedral field. Here, because it is a oxide, mixed oxide, so we have a weak field complex. It will be a high spin complex. So our metal will experience, it will be a high spin complex or a weak field complex due to the weak field ligand. And since my O4 occupied the CCP structure, that is why it is a octahedral field. So the splitting energy for the octahedral field for D, it will be something, it will be like so the splitting energy for D orbital in octahedral field is this is DG, this is D2G, this is D orbital, D orbital.
तो B3 का
This is my energy. So this is
smaller
D
size होता है ion का,
XY, DYZ, D ZX, and this is D X square minus Y square and D Z square. Okay, and the energy is this is 0.4 minus 0.4 del naught, and this is plus 0.6 del naught. Okay. So for the given metal ions for our question, we will find CFSE one by one, and then we'll determine which one is the inverse spinel. So first of all, nickel 2 is the electronic configuration will be written as argon 3d8, and for gallium 3, this is actually a non-transition metal. So this has a CFSE 0, and this one is definitely having CFSE minus 1.2 del naught. Correct? Yeah, so we have nickel plus 2 CFSE greater than gallium plus 3, and for this one belongs to our inverse spinel. Okay, but let's also have a look on other combination like zinc 2, that is the electronic configuration is argon 3d10. It has a CFSE of equal to 0, And Fe3, this has the electronic configuration as argon 3d5. It again has a CFSE as 0. So in this case, actually both are the transition metal, transition metal, and having CFSE equal to 0. Now we will go by size. So zinc has a smaller size in comparison to Fe. Okay, so zinc plus 2 will occupy the smaller void, that is the tetrahedral void here, and hence it will be a normal spinel. Okay, and third is Fe2 and chromium 3, and similarly you can find that the Fe2 electronic configuration is actually argon 3d6 having CFSE 0.4 del naught. Okay, with chromium having electronic configuration 3d3, so CFSE is minus 1.2 del naught, and hence it is again a normal spinel. Okay, because my divalent CFSE is larger than my trivalent metal ion. Okay. In the last case, Mn and Mn3, so my Mn2 is actually argon 3d5, and my Mn3 is actually argon 3d4. So this becomes CFSE equal to 0 and D4 is 0.6. Okay, so again this one is a normal spinel. Sorry. Okay, yeah. Because why? Because it has a higher CFS. So the given question has asked us about the inverse spinel among the given option. So we find out that the option number A is the correct one for the inverse spinel. And for this particular topic, I will highly recommend you to go through the lecture for lecture number 48, perovskite and spinels by Professor Madhav Ranganathan, Department of Chemistry, IIT Kanpur. I have also attached the link below. Thank you.
Yeah, so any of you have any doubt? So I will just clarify one thing. So I have said that smaller size ion will go to the smaller size void. So actually correction is there, because a smaller size ion will prefer to occupy the site of lower coordination. So lower coordination void is actually tetrahedral, and octahedral have higher coordination. So that is there. Also I have given 2 tips, so you can actually search in Google, and you will find that there is a particular table that people have made, that you can divide the d electronic configuration like d1, d2, d3, etc., for a transition metal to be in some normal or inverse spinel. So you can have a look for that also, or you can directly just go with the CFSE method, and have just 2 things in mind, that whether it is a transition metal, or if it is a non-transition metal, then the CFSE will be 0, and so that you can compare and then decide whether in that octahedral particular field, the whether it is a high spin ligand we are talking about. So obviously in spinels with oxide, it is a high spin and weak field. So yeah, that is there. So any doubt? Okay, so I will end this session now, and in future I think I can include one tutorial of if you guys are okay with it, because these kind of question are in further year also, but it's the same kind of calculation, but I can include how the octahedral and tetrahedral voids are there, what is the coordination number, and what is the difference between like HCP, CCP, these kind of small things. So I can include that separately without making a video or tutorial. Okay.
Madam?
Yes.
Just one. Madam, please send the video link, madam. That is spinal only, about spinal, madam. Spinal.
Link for the reference video. So you are asking for the link for the reference